So in the last lecture we discussed about what are the different kinds of joints. We made a sketch and showed you what are the different kinds of joints, how are they named after the shape of the connections between the brace and the chord. Brace is the branch which is taken from the chord, and usually the chord diameter is larger than the brace diameter, and chord thickness is generally larger than the brace thickness. So in this lecture we will talk about the ultimate strength capacity. Now before we start discussing this ultimate strength capacity, one can, let us say, expect some kind of an analytical model or a derivation for explaining the ultimate strength capacity. The moment we talk about plastic capacity or plastic models, we did a derivation, we made a mathematical modeling, then we analyzed and then we found out the equations. Unfortunately, as far as tubular joints are concerned, because of the complex interaction between the brace and the chord, it is very difficult to analytically model this behavior under the given combination of loads. So what essentially people have been looking in the past research is that if the brace is subjected to either tensile, axial tensile or axial compressive, what would be the ultimate strength carrying capacity or ultimate capacity of the joint as a whole. Most of the cases you will see in the literature, they have been always based on, these values are always based on the experimental results, because analytical modeling is difficult. I will tell you why. There are two important aspects why this kind of mathematical modeling is difficult. So the emphasis was made on estimating the capacity by conducting or fabricating these joints on 1:1 scale or scaled models and estimating the capacity in terms of the joint until its failure. We are talking about yield value, because in certain cases there has been difficulties of plastic section or plastic hinge formation after the plastic hinge is formed, because of the behavior or interaction behavior between the brace and the chord, and we all understand that the failure theory can be as complex as 5 numbers what we discussed in previous lectures. People are really not able to make out during analytical model, through analytical studies, that can we really find out the ultimate strength capacity of the sections. So people entirely focused, majority of the studies were focused on experimental results. Of course these results arrived at a summary which landed up in what we call empirical formulas. So we will discuss those empirical formulas as a designer's interest, instead of looking at how these equations would have been formulated or what would be the other parameters which will influence on this. So what I mean to say is, still there is a wider scope of research in this segment of estimating the ultimate strength capacity of tubular joints in terms of analytical numerical modeling. Still there is a large scope of research available in this sector, because most of the equations are derived based on experimental investigations, what we call them as empirical relationships. Okay, so we will see them as a designer's interest, because this course, as I told you, advanced marine structures is not talking about advancements in the marine structures, it is talking about the different applications of the design, selection of form, selection of geometry or analysis methodologies like ultimate strength design, plastic analysis, etc., reliability studies, fatigue analysis, etc. So the term adjective of advanced attached only to that kind of advancements. It is not talking about any fantastic or any, let us say, third generation or new generation offshore structures addressed in this course. This has been very clearly told in the first lecture itself. The advancement adjective is only attached to the method of analysis, method of understanding of the whole design process. Okay. In that context, as far as ultimate strength of the tubular joints are concerned, we are restrained to use the empirical relationships which are available in different codes, but I will put them all in one go in this lecture, so that this becomes a ready reckoner for a designer or the viewers to use this as an equation for finding out the capacity of the joints. Why we are focusing on joints? I think this question we already answered. We already know marine structures are highly indeterminate. In highly indeterminate structures like marine structures, take for example any offshore platform like a jacket structure or like a TLP or a spar, etc., where there are more number of joints, there are possibilities of plastic hinges being formed in these joints. If at all they fail, these hinges should have enough ductility or ductility strength, or let us say the ductility ratio, so that redistribution occurs and the applied load or the moment carrying capacity of the structure is enabled or increased by redistribution of these moments from the joints where plastic hinges are formed to the next successive critical sections, or the other section could also be a tubular joint. So tubular joints are susceptible for failure, that is number 1. So we look at this strength specifically. Number 2, our environmental load generally acting on marine structures are reversible in nature, maybe the velocity, maybe the wave height, maybe the direction, maybe the wind speed, maybe the wind direction, they can keep on changing throughout the service life of the structure system what we are looking at, open sea states. Therefore we are now looking for low magnitude high cycles of stresses or forces concentrating on the structure, and the worst part in a general structure is affected at joints. Therefore we have to look at the strength of the joints. The third aspect is most of the marine structures which are form innovative, for example triceratop, for example TLP as well, for example articulated structures, okay, you have deliberately introduced certain joints where there is a possibility of higher probability of failure at the joints, okay. So we have to look at these joints. So under 3 important stages or 3 important points we are concluding that ultimate strength capacity of the system basically or critically depends on the strength of the joints. Why tubular? Because most of our structural members are tubular in nature, we do not use any other section. Most commonly we use tubular because we need to have a large surface area, a high draft structure for heavy buoyancy, at the same time we do not have to have weight, therefore they are tubular structures. So mostly, so we are looking for ultimate strength tubular joints, okay. To start with we discuss with T joints. Let us quickly see how do they behave graphically in 2 nature of force like tension and compression. This is what we call as a brace, this is what we call as a cord, this is a T joint under compression. Is T joint there are some important observations we can make which is critical in both these behavior. Amongst both these behaviors, T joints under axial compression of brace is more critical, because it changes the curvature of the chord significantly. You can see the curvature of the chord is changed significantly, whereas in this case the chord is opened, okay, it becomes an open ring, the chord gets opened here, whereas here the curvature changes. So what happens in this case is, when such curvature changes occur significantly in the chord is subjected to stability problems. Okay. So the failure is a combination of plastic yield and the stability of the chord. So therefore we can say it is highly complex. Whereas in T joints under tension, the failure is either by plastic yield or rupture caused by shear stress. So here the chord gets separated at this junction, so I am drawing it here separately, and to oppose this there will be shear stress, and in this case to oppose this there will be shear force. So the chord will get disassociated, or the curvature of the chord changes significantly to the dotted line and then subjected to shear stresses. So in compression it is a combination of plastic yield plus stability problem of the chord, whereas in T joints under tension it is either plastic yield or rupture caused by the shear stresses. Obviously when the moment I say rupture caused by shear stress, the major shear stress will be only about 0.57 or 0.59, okay, 0.633 depending upon the theory of failure what we are using for the major shear stress, etc. So let us say this is my brace, which is imposing the force to the chord. The total force is P, we can say this is P by 2 and this is P by 2. So, if I cut open a section and see, subjected to axial force m naught and subjected to a moment m naught, and P by 2 is acting somewhere here. Let us say a variable of phi, and let us say this angle is alpha, and the shear flow and of course this is R. And the shear stress per unit length Q is P by pi R sin phi. This is a ring model for T joint in compression, because it is more critical. So, we are examining the joint in compression. Looking at this, we can understand that the chord ring is supported by the shear stress per unit length and we can say now the ultimate load of the T joint in compression is given by P ultimate compression the T joint. Please remember how I am writing it. P stands for the load, U stands for ultimate, C stands for compression. I am looking for compression. This stands for the T joint. Okay, that is how the symbol states. Empirically, this value is given by 7.5 beta mu T square sigma y, where beta is R by R, nu is R by T, of course sigma y is the yield value, and T is the thickness of the chord and small t is the thickness of the brace, small r is the radius of the brace, and capital R is the radius of the chord, and of course sigma y is the yield strength of the material. So, for a given design or for a given combination of the brace and chord thickness and the diameter, you know all these values. But one can easily see that this equation based on empirical calculations or empirical relationship is not valid for a wide range of beta and nu. Okay, there is a limitation of this validity. So, validity of parameters, what are the parameters? The parameters are in this case are beta and nu. Okay. .25 less than beta less than 0.85 and nu is 10 to 20. These are the validity, call this as 2. So, empirical relationships will always get combined with the validity of application in the design. To understand this, let us take 0.85 as beta. What does it mean is the brace radius will be approximately about 85% of the chord radius, or can be as low as 0.25 or 25% of the chord radius. It is, this equation is valid only for that combination of all. You cannot have a very small diameter brace with a very large chord, okay, cannot have this kind of a T-joint. Is that clear? So, it is all combined with a specific relationship. Similarly, even R by T is also combined. Can you tell me why this R by T is very important here? Can you guess me why R by T is important? R the radius of the chord and T is the thickness of the chord. Why we are talking about R by T here? As I said in the beginning, as far as failure of T joints and compression is concerned, stability of the chord is also important. Stability of the chord in this case is an R by T value, right? Okay, that is why nu is important here. This is for an empirical value which gives me the ultimate strength or ultimate load carrying capacity of a T joint in compression. Obviously, now we look for T joint in tension. Okay. Remember, the tension or compression is only the load applied on the brace, okay, not on the chord. Meaning of expression remains same still for all these parameters. The validity is changing. Zero point 0.2 to 1.0 and 9:30. I will call this equation number 4. Now, combining 1 and 3, we can get 1 is here and T is here. So, I can write an expression which says PUTT by PUCT is 2.3 plus 6 beta by 7.5 beta. Okay. I can plot this. This is PUTT by PUCT, and this is beta, and variation is like this. Let us talk about ultimate strength capacity of Y joints. Y joints can also be again in tension and compression depending upon what is the load applied on the brace. The typical Y joint, is what we call as a brace, this is what we call as a cord. This is my thickness of the cord, this is radius of the cord, and this thickness of the brace. This is I say small t, this I say capital T, this is I say small r, and this angle is phi. So, let us say this is subjected to compression or tension, let us say P. Okay. Now, Y joints in compression. Y joints will behave typically as same as T joints, provided I convert this force or the load applied on the joint to the normal to the direction of the axis of the cord. Okay, I just equally convert this to normal to the axis of the cord. I can apply whatever equation I had for T joints directly to my Y joint also. So, in that case I should say equivalent force which is P vertical, P sin phi, is it not, vertical force. I can call this as P U C Y. U stands for ultimate, C stands for compression, this Y stands for not yield, this is Y joint. Now I can say P U C Y can be simply P U T, okay, U C of T by because this is nothing but P U C of T. So, P U C of T already we know in tension or in compression, we already know this equation, we can substitute that. What is the value in compression for a T joint? It is 7.5 beta root nu T square sigma y by sin, equation number 5. The validity of the parameters 0.25, 0.85 is for beta, 10, 20 is for nu, and for phi it is 30, 90, equation number 6. Now I want to look for Y joint in tension. So I must substitute, let us say P u t y, that is tensile, is P u t t by sin phi, okay, corresponding tension. What is this equation? We already have it with us, this 2.3 plus 6 beta root nu t square sigma y by sin phi. And validity, I call this equation number 7, and validity point 2, 0.85, 10 to 30 and 30 to 90. Equation 8. Now experiments have shown that the T joints as a Y joints in tension have slightly higher capacity, therefore you have got to apply a correction factor to it. So experimental results suggested correction factor C applied to equation 7. What is the correction factor? So C is nothing but 1 plus sin phi by 2 sin phi, which is a function of the angle phi, which is the inclination of the brace with respect to the axis of the chord. Which is always greater than 1. Therefore, for phi of range of 30, C, can you give me what is this value? 1.5, isn't it? And for phi 90 is 1, isn't it? That is the validity of C. Therefore, the modified capacity of Y joints in tension can be P u t y is 2.3 plus 6 beta root nu t square sigma y one plus sin phi by 2 sin phi. To multiply this correction factor equation. There is something called punching shear stress, which applies at these junctions of brace and chords. It is actually nothing but the mean shear stress in the line which is between the brace and the cord. If you look at the figure, this is my member, punching shear stress will act at this junction. It will be tau. Now, as far as the behavior of brace cord is concerned, the punching shear stress is only a concept. In reality, the failure occurs by plastic yield. Let us look at ultimate strength of K joints. K joints have two types of connection. One is called as a one sided connection, other is called as a cross connection. Call this as phi 1, this as phi 2, maybe this is in tension, this can be in compression. And the gap between them is what I call as A, and the eccentricity between the intersection of the braces with that of the axis of the cord is what I call as F. And this is the cord diameter capital D, and of course these are brace diameters D1 and D2. We will talk about that why D1 and D2 are not very important. We will either consider D1 or D2, we will see why. This is what we call one sided K joint. Now there is something called cross connection, where the connection looks like this. is called cross type connection. Let us first look at the one sided connection. In a one sided connection you can always see that both the braces are connected to one side of the cord, whereas in cross type it is the other way, it is extending the other side. And the previous discussions of Y and T joints, we already seen that both of them are very critical as far as compression is concerned. Okay. When the compressive force applied to the brace, then they govern actually the design strength compared to the tough strength of the intention. So we will not consider this brace subjected to tensile forces, we will talk about this brace subjected to compressive force. So the common design practice is to consider the summation of the forces normal to the axis of the cord to be 0. In the cross type, instead of saying, do not say X type, it is cross type, okay, very specific, cross connection, because X type is another joint. In the cross type, the forces from one side of the cord should be transferred to the other side. That is the design principle here. I make a small modification in this figure, note it carefully. I say that let the angle of inclination of the brace which is having compression is phi 1, which is having tension is phi 2. So phi 1 is the inclination of the brace under compression. A is the gap between the braces. Some literature say this has a clear gap also, you can do it either way, is a clear gap between the braces, okay, this is A. F is the distance of intersection of brace line with or from the centroidal axis of the cord. This is F. Okay. So experiments conducted on this kind of joints, in case of one sided K joint, it showed very clearly that the failure is essentially governed by the compressive force, okay. Therefore they say the ultimate strength in compression of a K joint is similar to that of a ultimate strength on compression of an Y joint, because I am ignoring the tensile brace, it is like a Y joint, provided I multiply this with certain factors which are F1 of phi multiplied by F2 of beta multiplied by F3 of A. Now you can easily see F1 of phi is a factor influenced by the compression brace angle, remember that, compression brace angle. Which is given by 1 minus 0.26 cos square phi. I am using phi here, I am neither using phi 1 nor phi 2. You can always say compression base. Strictly speaking, in association to this figure, I must use phi 1 here. Okay, it is angle of inclination of the compression base. So I must use phi 1 there. F2 of beta is the factor influenced by the ratio of radius of brace and the chord. The moment I say brace, I must say here compression brace. Which is equal to if you have got two betas, what is beta? It is R by R, is it not? Beta is actually R by R. R is the radius of the brace and R is the capital R is the radius of the chord. So I can say simply beta 1 is R1 by R1 and beta 2 is R2 by, there is only one R, okay, where R1 is radius of the compression brace. So I must write here R1, whereas this is okay. So I focus only on the compression brace. So I get phi 2 beta as 6 point. Now I can clearly write this as beta 1 and beta 1 for our clarity. The third factor is influenced by the gap I will write it here. Oh, this is A, not G. This is what F3G is. I can make it as A, there is no G, make it as A, make it as A, we call the gap as A. So these are empirical formulas which will give you, let me call this equation number, will it be 8 or and all these three equations 10. All these three equations put together I call them as 11. So in this lecture we discussed about the ultimate strength capacities of various joints. We understood that compression brace is governing the design. Why we are not looking for analytical model or analytical behavior of these kind of joints? Because the failure is a combination of plastic yield as well as stability problems under compression. The moment you have stability problem, you have got PM interaction. We already saw in the last lectures that whenever you have got combination of loads, then the effect of one on the other is influencing. Therefore different theories say that different kinds of failure can occur. Okay. Therefore, extensive experiments have been conducted by researchers in the recent past, and they suggested lot of empirical values with the validity of the ranges which is given by the researchers. So what we are giving here is a summary of them, so that as a designer you can directly use them, but still there is a lot of scope for research in finding out the real behavior analytically, numerically and experimentally, validating them for different kinds of joints, for different parameters as beta, nu, g, etc. or a, etc. Okay, there are a lot of scope available, but as a designer we are now straight away using these equations. So in the next lecture we discuss about one of the type of joint, then we will move on to fluid structure interaction very quickly. Okay, or for a few minutes we can complete that also in this lecture. இங்கே இப்போ பண்ணிடலாமா, டேப் இருக்கா? Okay. Talk about the validity of range of the parameters. Beta is from 0.25 to 0.85, nu is from 10 to 55, a is from 0 to 0.6, and the brace angles 30 to 90. These are validities which I call them as equation number 12. These are all for your K joints. Let us talk about X joints. X joints look like this. Maybe both of them tensile, both of them compressive. There is a fundamental behavior difference between an X joint and a T joint, because T joint you may see the connection is only on one side, the X joint has got two, is it not? Let us highlight this difference, we will start, then we will speak about the strength capacity. In X joints, essentially the cord acts as a ring to transfer the force from one side to the other. It acts as a ring actually. Okay. Whereas in T joints the force transfer is by shear. So it shears off the moment it comes, it transfers here. Okay, it shears off. Okay, here the force transfer is by shear action. So there is a resistance offered in both sides the cord. So that is the fundamental difference between an X joint and a T joint in behavior. Therefore, the ultimate strength of X joint in compression sigma y you can call this equation number, what is the number? Whereas the validity .25, 0.85, and the ultimate strength in tension of an X joint is simply a factor of 1.48 to be multiplied with PUCX. So, you can very well see here in most of the experimental results it has been observed that the ultimate strength of any joint, be it Y, be it T, be it X, be it K, the strength is slightly higher compared to that of compression. That is why compressive force governs the design of tubular joints, because the failure is a combination of plastic hinge formation with that of the stability in case of T joints and S well, okay. And you will always see in case of Y, in case of K, they are equivalently converted to T. Then one can wonder what is the difference between a T joint with that of an X joint, where the brace is taken the other side of the cord also. In that case, here the behavior is the collar, the cord acts only as a collar or a ring just to transfer the force, whereas in this case the cord fails by shear, okay, that is the difference, okay. Now it is for your academic interest to compare which joint is better. If you have to provide a joint, what joint would be better? Of course it depends essentially on what is your functional requirement, whether you want to have brace on all the sides, you want to brace only on one side, etc. Other than that you can always compare. So this comparison has been done, it is available beautifully in the literature, you can see that how they vary in terms of its strength, okay. This ends this lecture on first module. So in the first module we have covered elaborately, starting from different forms and functions of offshore structures and marine structures, different materials used, environmental loading coming on them, what are the uncertainties involved in them, how uncertainties are handled, for example like incorporating aerodynamic admittance function, etc. Then we spoke about plastic analysis and design, lower bound and upper bound theorems, kinematic and static theorem on the other hand. We compared them, we did problems on beams, on frames, then we also find out what is actually the safety part involved in plastic design compared to the tough conventional design, and how to estimate that from problem. We did some numerical examples to understand them, how to pick up the highest or the lower bound values, how both the theorems are important, then what is the uniqueness theorem which is a combination of these two. Then we studied about different theories of failure, and we understood in detail what would be the significance of estimating sigma y as my yield strength at failure. Then we spoke about the capacity of joints in terms of, and we also studied fundamental concepts of impact analysis on marine structures. So this ends the discussions on first module. The next lecture we will pick up lectures on second module. Thank you.